All right, can you guys hear me okay? Okay, so as many of you realize, I am not ULAS. I'm Dave Chandler, as you mentioned, from Microchip. I'm a product line manager for System Atomic Clocks. I'm just going to give a brief overview. Looking around the audience, a lot of you guys have probably seen a lot of this material before. As a matter of fact, most of you guys normally present at the same conferences with me, so it might be a little bit of a repeat, but just going through it anyway. We're going to talk about the need for time, why we have distributed data. We're going to talk about how we translate the need for the timing into transactions per second. How does that bridge occur? We're going to talk about typical time dissemination approaches and then dealing with GNSS outages. So first, why do we do distributed databases? Again, I think a lot of you guys understand that, but you know, global computing power now is about need for about, I think it's what, 1 zettabyte. 1 zettabyte is a 1 with 21 zeros after it. If you can imagine, we're processing that much data today. That's pretty incredible. And AI, I had to put it in here because everybody has AI in their presentations. So I have my bullet about AI. It's causing the demand to exponentially increase. You know, it used to be for about 40 years, it just didn't matter. Anytime we needed to increase capacity, it was like, okay, well, the silicon can always catch up, right? Silicon was always doubling the number of transistors we can put in. That increased the capacity and the speed. We didn't have a problem. But, you know, that was Moore's law. Unfortunately, the atom repealed it, right? You know, you got to a point around 2010 where the pitches started to get to the same size of the diameter of an atom. Now you can't make things smaller. If you can, you're dealing with quantum effects. So we were stuck, right? And the solution to that was we all went to horizontal scaling solutions, right? Our networking gear, you know, this box right there, got so good that we could really take 1,000 servers and make one giant virtual machine so it could still handle our databases. So once we did that, the next issue we had to overcome was how do we manage global demand, right? Unfortunately, you know, let's say I have somebody in London and somebody in San Jose. I have a real speed limit here. And until somebody actually gets, you know, spooky entanglement working, I'm stuck with 670 million miles per hour in order to transfer data back and forth. The example is San Jose to London. It's 5,630 miles. That's 28 milliseconds, which is really, really slow, right? So if we look at that, you know, a round trip would be about 60 milliseconds. Real world is much worse than that because you have to worry about things like refractive index and refractive index of the fiber. You're looking about 3-4 times worse than that. So you're up to 250 milliseconds. It's allowing me to do 4 round trips in a second. Obviously, it didn't work for us. We had to come up with solutions. So we went to replicating the database, or at least the stuff we needed, in multiple places next to the edge. So, you know, here we have the example of what we did. We said San Jose, London, we'll replicate the data. You know, maybe we put another one over here in Timbuktu. Doesn't matter. We got multiple replicants happening. And basically, you know, now we have one giant virtual global machine. This is an ideal case, but, you know, it's what people are trying to get to. Some of the big hyperscalers are doing this today. When you do that, and I know some other people have talked about that today, but you actually have issues then with causality and, you know, which record was written to first. If it's the same record or if they're causal records, that can be a problem. So with an ideal time source, when we only had one box and an ideal time source, who cares? You don't really need to worry about it. But, you know, there's no such thing as an ideal time source. And we're obviously now dealing with thousands upon thousands of machines located around the world. So I'll give you an example of why the causality thing. I like using this one. But let's imagine I had a 100-meter dash that was being run. And, you know, 2 records here, the start time and the finish time. And in a, you know, absolute perfect clock, you can see down here it's about 9.6 seconds. It's obviously a gross exaggeration. If you have a plus or minus 5-second clock in your database or in your data center, you should be fired. But anyway, the clock starts 5 seconds fast. That means the start time is actually recorded as like 12:05 in this case. Finish time's 5 seconds slow. Now I, you know, finished before I started. I have a bunch of people who are still waiting at the finish line even though it's over already. So that's the issue of causality I like to talk about. I do want to point out not every record is causal. You know, there's some records, it just doesn't matter what they occur in, and so there's some fixed probability on that. But then you have things like mathematical records on the same record, or maybe they're related records. Those things you actually have to worry about the causality. This is an everyday example of what happens when you have causal problems. You run into conflicts. This happens once a week to me when I go into SharePoint. I do I update my weekly report for my boss, and one of my peers, who some of you guys know, Will Kurzwick, is updating his. Guess what? I'm trying to update in SharePoint. We get these annoying messages. When we're dealing with SharePoint and PowerPoints, who cares? It's, one of us is going to lose out, but it's an annoyance. But, obviously, when you're doing multiple records, you can't have human intervention, and you're going to make a decision. And honestly, there's no correct decision in this case. You're just throwing away one of the datas, right? You can try to do a whole bunch of things about, okay, well, 10 records say this and only 2 said that. Bottom line is, there's still no correct decision. You're just doing the highest probability. So in order to do that, we have to have a good external time reference. How we get around this is by making sure everybody has the same time or close to it. For our global databases, we normally do this by getting GPS, and we distribute that down to our data centers. Then we look at it with, OCPTAP in this case is what I'm talking about. NTP-PTP goes down, from the inside of the data center to the individual servers. Then we also have to worry about from the NIC to the app. What's actually, what's the speed there? That's something else you have to worry about. And on top of GPS, you can have other time sources, right? I have a cesium unit here. We could have, something from a national time lab. You could have lots of other time sources coming in, but ultimately they all have to be consistent by the time I'm looking at each one of those data centers. So looking at this, the OCPTAP spec is plus or minus 2.5 microseconds by the time you get to the app. So they all have to be plus or minus 2.5 from UTC, which in this case, I'm showing Timbuktu to San Jose. If I'm plus or minus 2.5, that gives me 5 microseconds maximum. So what do I get with that 2.5? Well, if I look at that, the best thing I can possibly do is have, I'm only showing 25 microseconds here, and I see best thing I can possibly do with plus or minus 2.5 is 5. Over 1 second, I have the maximum best rate I could have without any overlapping ambiguities would be 200,000 non-overlapping envelopes per second. I like calling them envelopes, not windows of uncertainty, because I have a timestamp in the middle. I don't put stamps on windows, I put them on envelopes. But anyway, when you look at that, pretty simple formula. Envelopes per second is just 1 over twice the clock uncertainty. And this is an absolute best case scenario, right? That's the most you could get in with that clock uncertainty without having to worry about irresolvable ambiguities. But what you can do is you can increase the EPS, right, by making the clock window smaller. But every time you do that, it's just more expensive. And oh, by the way, you can never completely eliminate the chance of an overlap, right? Because something could still be within those windows, but you're just trying to make it better and better to decrease the probability. But now, and when you do have an overlap, the problems it creates is the computing power. You need extra computing power. You're going to have to roll back some of the data, and you're increasing the data corruption. So you got to consider all these things when you're doing your timing base. Ideally, everybody would love to have a mazer with maybe White Rabbit going to every server. That's great, but it's not realistic. So you have to look at things like what's the probability a record will be written to, at the same time at 2 different locations. What's the criticality of doing a rollback? In some cases, if it's a military application, that could be pretty important, right, if you're tracking something. So anyway, there's just lots of things you have to take into account. What I try to tell people when they're working in databases, because I still have a lot of people say, well, what does it mean for me? You're telling me I can do 10 picoseconds or 1 microsecond. What does it mean? General rule of thumb, you could compare your TPS to EPS and say, yeah, I want them about the same. It's going to give me, a decent performance. I'm going to take out a lot of the ambiguities. There'll still be some. But, maybe that's expensive. Maybe it's not expensive in your application. What I like to do to tell people is wait. What is a criticality when I have an inconsistency? Put a weighting scale on it. Some applications, could be, health, military, could be really critical. Other applications, let's say it's Facebook, oh, well, we just rewrite it. It's a minor annoyance. Also, peak transactions, probabilities of writes. You can put all these things in weighting scales and come out with the weighted TPS and just basically say, all right, I want my envelopes per second to be greater than my weighted TPS. Okay, going from that, So what's the timing budget that's in the OCPTAP profile? When I talked about that 2.5 microseconds, this is how it's broken down, plus or minus 100 nanoseconds at the OCPTAP cards, right? That's going to GPS. I got 800 nanoseconds in here from my NTP or my PTP going to the servers. Then I got 200 nanoseconds from the NIC to the app. One thing I would like to point out is last year there was a really good presentation by a gentleman from Intel who basically said, this is really overly optimistic. You know, fully loaded servers, it could be as bad as 2 microseconds in there. And I apologize for that. I thought I turned those off. Anyway, so as I look at that, it doesn't add up, right? You're looking at 1,100 nanoseconds. Well, what is everything else? Everything else is holdover, right? The situation where I lost my time source. And essentially, OCPTAP's allowing me 1,400 nanoseconds over 24 hours. What happened here? I'm frozen. There we go. So, ugly formula. Not going to go into it in detail. But basically, the formula here is, there we go. Okay. The formula can be broken down, it's environmental effects, it's aging, it's training, how did I discipline it, frequency offsets. Basically what I did to model this, and people can do it different ways, but I took the aging component as a deterministic variable. Basically it can be predicted based off the spec sheet. Then I threw everything else into random variables. So I threw off, I put the training, which is really how good my frequency offset is based off of my reference that I trained to, and my noise term, which is just fundamental to the clock. But I also threw temperature into the stochastic area, the random variables, rather than where you see it a lot of times, someone puts it in deterministic, because I'm basically saying you can treat temperature, it's going to vary randomly while you're working on things. So I threw it in here in a stochastic where we take, the sum of the squares and take the square root of that in order to get that difference. So anyway, if I look at that, what does it tell me? Well, I looked at 3 common holdover options here, an OCXO, rubidium, and a cesium. Took data from the data sheets or from my personal knowledge of working with these things for 27 years. Threw in what I expected. I set a random temperature variation, plus or minus 2.8 degrees C, which is 1.77 RMS. So I then took, what was published or what I knew the actual temperature coefficients were for these devices. I looked at how good I thought we could discipline them and what the variation was at that point, and also what the aging is, and I graphed it. So basically an OCXO comes out to 12 hours for 1.4 nanoseconds. If I look at the OCPTAP requirement, it actually says 1 day. So an OCXO on its own wouldn't make it. Now, there are better OCXOs. This was just an example. And you can also remove some of that deterministic component. So some OCXOs are going to come pretty close or maybe even meet that. But this is just completely uncorrected. You can see a rubidium here does 50 hours, and a cesium does 560 days using that formula. Anyway, what do I get with all that? So basically, 2.5 microseconds is 200 kilo envelopes per second. And so that's telling me, again, the rubidium's going to do about 48 hours. I had 50 over there plus for a 2 sigma value. Whereas a cesium over 2 years is going to give me about, it's going to give me about 2 years. One thing I do want to point out is if I looked at the cesium over the same time frame as a rubidium, I'd actually wind up with 400 kilos, being able to do 400 kilo envelopes per second in this case, and that's all because the cesium basically isn't moving over those 2 days, and I can, at least at these scales, this becomes what's limiting me up here. All right, so what's next? So we have some big improvements coming up for EPS, right? And stuff that's realizable today. We can probably get to about 10 million envelopes per second, plus or minus 50 nanoseconds is something we can do and something we should be striving to. Now remember, we are talking thousands of clients too. We're not talking 1 or 2 units. But basically, with PTM, we're able to get about 20 nanoseconds from the NIC to the app. I put 10 nanoseconds in here for PTP, high accuracy. a lot of people are going to say, hey, you can be in the picosecond range. I'm taking into account there may be multiple hops, there may be 1,000 clients or more. So it's just, what's realizable today. And we have GPS receivers that relatively easily can do plus or minus 5 nanoseconds a day. So that leaves me with about 15 nanoseconds of holdover. Looking at the two devices I showed you before, one is a rubidium. It would do about 1 hour at that level, which really isn't a lot of holdover. And if I look at a cesium, now I'm getting 6 days with a cesium. So that just gives you a rough idea of, if we tomorrow said 50 nanoseconds, we have all this technology. It's not overly expensive, maybe with the exception of this thing, if you're having to, put it in every data center, but people do. Anyway, what's next? So as we continue to work, getting the timing down, and we've already had a couple of presentations on what's next, but basically, physicists have had much better clocks in their labs for years. They basically went, there are problems with those. These things are doing the 1e to the minus 18 numbers, the 1 second over the life of the universe. Problem is, the ones that are in the labs are too expensive. They don't fit in a rack a lot of times, right? Or they had environmental sensitivities. They were only meant for lab use. And the last thing is you need Sheldon Cooper and Leonard Hostetler to operate these things, right? Not everybody has a bunch of physicists on staff. But there are new clocks that are either close to release or in their early life cycles. I think you saw probably 1 or 2 of them over the last couple of days. Some of them, there are microwave clocks, which are what we're using as atomic clocks today, but we're getting order of magnitude improvements off of them. Things like pulsed rubidium, ion clocks, cold atoms. These are all newer technologies that essentially make the query. They're improving either our signal to noise or the interrogation time. And what that does is it gives you a more precise clock. So these are going to get us about an order of magnitude better performance. And then we have the true optical clocks that are out there. There's a couple of technologies being used that sound really cool. One's 2-photon rubidium, another one's molecular iodine. These clocks actually are, operating at the terahertz range, so they're, quantum improvement on that level. Some cases, a signal-to-noise ratio is lower, so you may only be getting 2 or 3 orders of magnitude improvement, even though the Q is much, much smaller. But that's what's coming up. And what I would like to say is there's a really good article by Schmidberger and Schur, but it's kind of old, needs to be updated at this point. They published it about 4 years ago, said this is what's available. And what you'd find in that paper, these things are actually very well defined. And what I was going to try to do is say, well, what do I get with these guys in here? But what I found was looking at his paper, didn't really see enough data points on the aging and the temperature coefficients, and going through a lot of the presentations, I still don't see hard numbers. I know they should be better in a lot of cases, particularly the environmental sensitivities, but you don't often see somebody getting up there and saying, hey, it is really 1e to the minus 15 over temperature or something. Also, the aging, you don't really see that in a lot of presentations. Sometimes it's removed, but it's deterministic, so it could be removed. They just didn't have enough information to put in the graphs. Anyway, that's all I had. Any questions? Oh no, you're going to ask me about, what was it, inconsistent data entanglements or something?
Well, I really liked your characterization of the problem timestamps as an envelope problem. And the reason is because it's impossible to actually define the endpoints of an interval on a blank Minkowski background of space-time. It's like impossible. You don't know where the starting point is. So thank you for that. That's a really insightful way of looking at transactions better. However, I did notice an error in your holdover formula. Okay. Actually, there were 2. One of them was that it's based on continuum mathematics, and so if you're trying to measure something on a real line, and our computers can only measure things with integers for the time counter or the integers that we're exchanging between Ethernet packets, then there is a big discrepancy here between a smooth background, which is impossible to know precisely, and a discrete measurement that we're making. The second point, which might be closely related in your answer, is that when you take the sum of the squares and then you take the square root, then you actually end up with this, this number called I that ends up in there somewhere, which means that you have to take into account plus and minus and not just plus.
Absolutely. So along those lines, let me see, your first question was doing a continuum. You're absolutely right, because I'm looking at it as a physicist. At heart, I'm a physicist, and the physics of those devices are continuous. The realization of it in a data center is what gets, when you're using it at your computers, yes, it gets, chunked into discrete intervals. So yeah, there is some other things that need to be taken into account there, no doubt. The second question, can you repeat it again?
Yeah, so first one was the continuum question.
Yes.
I'm just highlighting an assumption so that we can all think about this. And the second one was related to
the I term.
I. It's
Yeah.
like if you're doing the sum of the squares, then you end up with plus and minus.
Absolutely.
And you can't just
Right.
one of them out and say everything's positive, monotonic.
So what I showed when I did the sum of the squares, and I did a mu plus 2 sigma, right? What I'm showing is adding them up, as all being in the same direction. That should be a worst case envelope, right? You still have to worry about whether it's going on this side or this side, and each one of those, as well as the aging could have been this way as well as something negative. So it is still a plus or minus number, absolutely. The other thing you have to worry about with those sum of squares is they are still, probabilistic in nature. So you're still looking at my window, that I put in there, my nice even stamps, that's only at 2 sigma or whatever I'm defining. There's still a finite probability it could be outside those, and I still have problems.
So in the interest of time,
Yep.
let's move on to the next presenter. Ulas